In the cold dark beyond Jupiter, a moon covered in cracked ice just whispered back at us. James Webb turned its mirrors on Europa for the very first time, and what it saw made scientists go quiet. Salt rising from a hidden ocean, carbon dioxide where none should be, chemistry so strange it broke the models. Tonight we step onto a frozen shell hiding a sea twice the size of Earth's, into chaos terrain that moves, past radiation that would kill you in minutes. If wonder like this keeps you up, hit that like and subscribe button now. Prepare yourselves. We begin. Picture a telescope the size of a tennis court, floating 1 million miles from Earth, suddenly tilting its golden mirrors toward a small, icy world circling Jupiter. That moment happened, and the data it sent home shook the people who opened it. Europa is not large. It is slightly smaller than our own moon, but it has been the prime suspect in the search for alien life for almost 40 years. Beneath its frozen crust, scientists believe, lies an ocean of liquid water, salty, dark, possibly warm at the bottom, possibly full of chemistry that life would recognize. The problem has always been the same. We cannot see through the ice. Every telescope before James Webb gave us blurry hints, splashes of color, smears of mystery. The Hubble Space Telescope tried for years, and Hubble is brilliant, but Hubble sees mostly visible light. Europa's deepest secrets hide in the infrared, heat fingerprints, chemical fingerprints, the kind of light Hubble was never built to read clearly. James Webb was. That was the entire point of its design. An infrared eye so sharp it can pick up a candle on the surface of the moon from your front porch. So, when Webb turned toward Europa in 2022, the team running the observation did not know what to expect. They had only a few minutes of telescope time. A few minutes is nothing in astronomy. You usually need hours. Heidi Hammel, the scientist leading those first observations of our solar system, has confirmed this in interviews. They were stunned. In those few minutes, Webb pulled in more useful chemistry data on Europa than decades of older missions combined. The infrared signal was clean, the fingerprints were sharp, and one fingerprint in particular did not belong there. A team back on Earth was huddled around the screens. They expected mostly ice, water ice, maybe some sulfur compounds blasted onto the surface by Jupiter's radiation. What they got instead was a chemical map, a map showing one substance pooling exactly where the ice looked the most disturbed. One geologist on the team reportedly said the data felt wrong. Not wrong as in broken, wrong as in alive. The image that came back was not pretty. It was not the glossy postcard the public usually sees. It was a series of colored panels showing different wavelengths of light, each one peeling back a different layer of Europa's skin. And in those panels, a story started to form. A story of a world that is not sleeping under its ice. A world that is leaking. A world where something underneath is pushing up. Now here is the part that gave the room chills. The chemicals Webb spotted are not stable on Europa's surface. They cannot last there. Jupiter's radiation should destroy them in a geological blink. So whatever Webb saw had to be fresh, recently delivered, pushed up from below in the last few million years, which is yesterday in cosmic terms. That single fact rewrites the entire mission. It means Europa is not a museum piece. It is a living chemical engine, and we just caught it in the act. But to understand why this is horrifying as well as exciting, we have to go to the one spot on Europa where all the strangeness is concentrated. A region with a name that sounds almost gentle. Terra Regio. Imagine taking a frozen lake, smashing it with a hammer, then letting the pieces refreeze at slightly wrong angles. Now scale that up to the size of a small country. That is Terra Regio. It sits near Europa's equator, a stretch of terrain that planetary scientists call chaos. The name is not poetic exaggeration. It is a technical classification. Chaos terrain is what you get when the ice shell of a moon has been broken, rotated, partially melted, and refrozen, sometimes more than once. From orbit, it looks like a jigsaw puzzle where someone forgot how the pieces fit. Europa has several of these chaos regions: Connemara, Murias, Aran. But Tara Regio is the one Webb stared at the hardest. And Tara Regio is the one that gave up the biggest secret. Before Webb, the Hubble Space Telescope had already noticed something odd here. Hubble picked up the chemical fingerprint of salt in this exact region. Specifically, sodium chloride, the same compound you sprinkle on your dinner. That alone was a clue, because that kind of salt on the surface of an icy moon does not usually come from nowhere. It tends to come from below, from a liquid source. When Webb pointed its instruments at Tara Regio, the salt story got stranger. Not only was the salt still there, but now there was carbon dioxide pooled on top of it, and not in a thin, even dusting. In a sharp concentration, right inside the chaos zone, fading out as you moved into the older, smoother ice around it. This is the first hint of why scientists started using words like horrifying, not because anything attacked them, because the pattern is too clean, too deliberate. The chemistry is concentrated exactly where the surface looks broken open, like a wound, like something is bleeding. Now here is the simple way to picture it. Imagine you found a perfectly preserved spot of fresh paint on an old rusted car. You would not assume the paint blew in from the sky. You would assume someone painted that exact spot recently. Tara Regio is the fresh paint. Whatever painted it is hiding under the ice. The team, led by Geronimo Villanueva at NASA's Goddard Space Flight Center, has now confirmed this through papers published in the journal Science. The carbon at Tara Regio is from below. It was deposited recently, and the chaos terrain is where the inside of Europa is leaking to the outside. That word, leaking, is doing a lot of work, because if Europa is leaking, then the ice is not a perfect lid. The ocean below and the surface above are talking to each other. Material is moving up. Maybe material is moving down. And down is where it gets interesting. Down is where the warm, dark water sits. Down is where life on Earth first appeared, around hot vents on a black sea floor, billions of years ago. If Tara Regio is a window into that down, then we are not looking at a dead moon anymore. We are looking at a chemistry experiment that has been running undisturbed for 4.5 billion years. And the first ingredient Webb identified in that experiment is the one every astrobiologist had been waiting for. Carbon is the element of life. Every living thing on Earth, from blue whales to the bacteria in your gut, is built around carbon atoms linked together. That is why finding carbon on another world matters so much. It is not proof of life, but it is the building block. Europa had always been missing this part of the story. Scientists were sure about the water. They were almost sure about the energy. But the carbon, the key ingredient, was unproven. Until Webb. What Webb detected in Tara Regio was carbon dioxide, frozen, mixed into the surface ice. A few minutes of observation was all it took. The chemical fingerprint of carbon dioxide in infrared light is unmistakable. It vibrates at a specific frequency that nothing else on Europa's surface fakes well. The signal was clear, the signal was strong, and the signal was in the wrong place. That is where things get strange, because carbon dioxide on Europa's surface should not survive. Jupiter blasts that moon with radiation so intense it would kill an unshielded human in about 20 minutes. That same radiation tears apart molecules. It breaks down carbon dioxide quickly in geological terms. Within a few million years, any CO2 left exposed should be shredded back into its component atoms and scattered. So what Webb saw should not have been there, not unless someone or something was constantly replacing it. The team ran the math. They looked at the concentration, they looked at the radiation environment, and they concluded that the carbon dioxide must have been delivered to the surface in the last few 100,000 years, maybe less. In cosmic time, that is the equivalent of finding warm footprints in the snow. Something walked here recently. Now, the obvious question. Could that carbon have come from outside? Could it have been delivered by a comet impact or a meteor carrying carbon compounds? Both possibilities were checked. Both were ruled out, or close to it. Comets and meteors hit moons randomly. The carbon dioxide on Europa is not random. It is concentrated. It is mapped to a specific region of chaos terrain, the same place where salt from the deep ocean is also rising. That pattern does not match an impact, it matches a leak. Samantha Trumbo at Cornell University, the lead author on the second paper describing this finding, put it bluntly: carbon is a biologically essential element. Finding observational evidence that the carbon on Europa's surface came from the ocean is not a trivial thing. Her quote stuck because it carried weight no headline writer needed to exaggerate. Here is what that means in plain language. Europa's ocean is not just water, it is water with carbon in it. The ocean is chemically rich. It has the raw ingredient life needs to start. We did not have that confirmation before. We have it now. Picture it this way. For decades, we knew Europa had a kitchen. We knew it had pots and pans, meaning water and energy. What we did not know was whether the kitchen had any food in it. Webb just walked in and found the pantry stocked. But carbon alone is only the beginning. The next thing Webb found was something even harder to explain. Something nobody had expected to see. The next question scientists faced was simple. Carbon on the surface, yes. But where did it actually come from? There are only three options. The carbon could have been delivered from space, by comets or meteorites carrying carbon compounds. It could have been produced on the surface itself, by radiation chemistry breaking apart other molecules. Or it could have come up from the ocean underneath. Each option leads to a very different Europa. So the team had to be careful. They had to rule things out one at a time, the way a detective rules out suspects. Start with comets. Comets do carry carbon. They are basically dirty snowballs full of organic compounds. And when they hit a moon, they scatter their chemistry everywhere. But scattering is the key word. A comet strike leaves a crater, and the carbon ends up smeared in a radial pattern around the impact site. Webb saw nothing like that. The carbon on Europa was tightly clumped into Terra Regio, the chaos region. No nearby crater explains the pattern. No nearby crater is anywhere near big enough. Comet origin ruled out. Now, consider radiation chemistry. Jupiter throws so much radiation at Europa that the surface ice gets bombarded constantly. That radiation can take ordinary molecules and turn them into something else. It is possible, in principle, for radiation to cook up carbon dioxide on the surface if there is already carbon there to start with. But there is the problem. You need a source of carbon already sitting on top, and we had no evidence of carbon-bearing material being delivered to Europa in any large quantity from outside. Radiation alone cannot make carbon out of nothing. It can only rearrange what is already there. So this option was also weakened. That leaves the third possibility. The carbon came from below, from the ocean. This is where the chemistry locked in. Webb did not just measure the amount of carbon dioxide. It measured the ratio of two different kinds of carbon. There is a common version with 6 protons and 6 neutrons in the nucleus, called carbon-12, and there is a heavier, rarer version called carbon-13. Living things on Earth tend to favor the lighter version. Geological processes tend to mix them in certain predictable ways. Comets leave their own ratio behind, different from Europa's mantle. The ratio Webb found on Europa was consistent with an internal source, meaning the carbon came up from inside Europa itself, most likely through the ocean. The signature did not match a comet. It did not match dust from interplanetary space. It matched material that has been sitting inside the moon for a very long time. To picture it, think of a sealed jar with mud at the bottom and water above. Over time, gases bubble up from the mud, dissolve in the water, and then escape through tiny cracks in the lid. The lid is the ice shell. The water is the ocean. The mud is the rocky seafloor we cannot see. Webb just caught the gas leaking out of the lid. That changes what Europa is. It is not a frozen ball with a hidden lake. It is a living chemical reactor connected to its own atmosphere, however thin that atmosphere may be. And once you accept that Europa has a connection between its hidden ocean and its surface, every other discovery starts to slot into place, including the one that surprised everyone the most. A simple, Familiar chemical, in the wrong place. A chemical you can taste at any dinner table. Stop for a second and imagine this. You are standing on Europa's surface. The sky above is black. Jupiter looms huge on the horizon, taking up an enormous patch of the view. Beneath your boots, you feel solid ice. But the ice is not bedrock. It is a frozen lid, somewhere between 3 and 20 miles thick. And below that lid, going down for 60 more miles, is liquid water. That is the ocean we are talking about. 60 miles deep on average, possibly deeper in places. It wraps the entire moon. There is no shoreline. There is no continent. The ocean is one connected body covering every square foot of Europa, sealed in by ice above and rocky seafloor below. Earth's oceans, the ones that hold all our whales and coral reefs and shipwrecks, average about 2.5 miles deep. Europa's ocean averages around 40 times deeper. The total volume of liquid water on Europa is estimated at roughly 3 billion cubic miles. The total volume of liquid water on Earth, including every ocean, lake, and underground reservoir combined, is somewhere around 340 million cubic miles. Roughly twice as much liquid water sits on this small moon as exists on our entire planet. Let that picture land for a moment, because most people do not realize it. Earth, the blue planet, the so-called water world, is outclassed in water by a frozen moon smaller than our own. The solar system's biggest swimming pool is not here. It is out there, hidden under ice. How do we know any of this without ever drilling through the surface? The proof came from a spacecraft called Galileo, which orbited Jupiter from 1995 to 2003. Galileo flew past Europa many times, and each time it measured the moon's magnetic field. What it found was strange. Europa was generating a magnetic response that could only be created by a layer of electrically conductive material inside it. Salty liquid water conducts electricity. Frozen ice does not. The signal told scientists, with high confidence, that something liquid and salty was sloshing around inside Europa. Then came Webb, decades later, adding the chemistry to complete the picture. Salts on the surface, carbon dioxide leaking up. The two readings together, magnetic and chemical, lock the answer in place. The ocean is there. The ocean is salty. The ocean is talking to the surface. Now here is the part that turns wonder into unease. We have no idea what is in that ocean. None. Every measurement we have is indirect. We are reading fingerprints on a window. We have never seen what is in the room. On Earth, wherever there is liquid water, there is life. Every drop of seawater contains living cells. Every cave pool, every hot spring, every freezing crack in Antarctic ice. Life finds water and moves in. There is no known exception on our planet. Europa has water by the cubic mile. Europa has carbon. Europa has salt. Europa has an energy source from Jupiter's tides squeezing it constantly. Every box that gets checked on the habitability scorecard, Europa is now checking. We are not saying there is life there. We are saying there is nothing on the list that would forbid it. And the next discovery makes the case even harder to dismiss. When Webb first looked at Terra Regio in detail, scientists were not just hunting for carbon. They were also confirming something Hubble had seen years earlier. Salt, specifically, the same kind of salt you sprinkle on French fries. Sodium chloride, common table salt. The chemical fingerprint had been detected by Hubble back in 2019, but Hubble could not say with full confidence what it meant. The signal was faint. The interpretation depended on other chemicals being present or absent. Webb's job was to clean up the picture, and it did. What Webb confirmed is that sodium chloride is concentrated in the same chaos region where the carbon dioxide is. The two chemicals are sitting on top of each other. They have the same fingerprint pattern on the surface. They are clustered into the same broken icy area, and neither of them belongs there. Sodium chloride is not a chemical you get from interplanetary dust. You get it from a salty ocean, the same way you get salt deposits on Earth, by water carrying dissolved salt up from below and leaving it behind when the water freezes or evaporates. Picture a coastal cliff where the sea has splashed up for thousands of years, slowly building a salt crust on the rock. Terra Regio is essentially that. On a moon, the ocean below is heaving material upward through cracks in the ice. The water mostly freezes back, but the salt it was carrying is left behind on the surface, painting the chaos region with a slow, accumulating signature. Richard Cartwright of Johns Hopkins Applied Physics Laboratory described the chemistry of this region as strange and exciting. That word choice matters. He is a spectroscopist. People in his job do not throw around the word strange casually. They use it when the data does not fit any clean expectation. Here is why his team called it strange. Sodium chloride is not the only salt you would expect from a planetary ocean. Magnesium-rich salts should also be present in large amounts, based on models of how Europa's seafloor should weather over billions of years. But Terra Regio is dominated by sodium chloride. The expected magnesium salts are weaker. That suggests the ocean's chemistry has been shaped by something specific. Maybe hydrothermal activity at the seafloor. Maybe an unusual rock type underneath. Either way, it tells us the ocean is not generic. It has a personality. It has a history. Now combine the salt with the carbon. Together, they tell a story. The Europa Ocean is salty in a way that resembles the deep oceans of Earth more than anyone expected. It contains the carbon needed for biology. It is leaking both of those signatures to the surface through the chaos terrain. And it has been doing this on a timescale recent enough for the signals to survive Jupiter's radiation. This is the moment where careful scientists started using careful words. Habitable. Compatible with life as we know it. Astrobiologically interesting. They will not say life. They will not even hint at it without 10 layers of qualification. But the language has shifted. Before Webb, Europa was a hopeful candidate. After Webb, Europa is the leading candidate. And the next chemical Webb spotted in that same patch of chaos took even hardened scientists by surprise. It was not just unusual. It was almost impossible to explain. Hydrogen peroxide is the stuff in the brown bottle in your medicine cabinet, the same liquid that fizzes on a cut. On Europa, it does something far stranger. It tells us where the ocean might be reaching the surface. Here is the background. When Jupiter's radiation hits the water ice on Europa, it can split water molecules apart and reassemble them into hydrogen peroxide. This has been known for years. The interesting question was always, where on Europa would you find the most of it? The intuitive answer was the poles. The poles are colder. Hydrogen peroxide is more stable in colder temperatures. So, you would expect it to accumulate at the top and bottom of the moon, where the ice is freshest and the temperature is lowest. Webb checked, and what Webb found broke the prediction in half. The highest concentrations of hydrogen peroxide are not at the poles, they are at the equator, specifically in Terra Regio, the same chaos region where the carbon and the salt are also pooled. The warmer equatorial belt, which should have less hydrogen peroxide based on simple chemistry, somehow has more. This was not a small surprise. This was the kind of result that makes a team check their instruments 3 times before publishing. The polar prediction had been the working assumption for decades. Webb essentially flipped it. The puzzle stayed unsolved until 2024, when a graduate student named Bereket Mamo at the University of Texas at San Antonio, working with the Southwest Research Institute, decided to try recreating Europa's conditions in a laboratory. He cooled ice down to European temperatures. He added trace amounts of carbon dioxide, the same kind Webb had detected. Then he blasted the ice with radiation, similar to what Jupiter dumps on Europa. The result was startling. The hydrogen peroxide production jumped enormously. Adding even a small amount of CO2 to the ice supercharged the chemistry. Carbon dioxide acted like a catalyst, opening pathways that did not exist in pure water ice. That solved the geographical puzzle. The hydrogen peroxide piles up at the equator because the carbon dioxide is at the equator, and the two chemicals reinforce each other. Polar ice without that carbon boost, makes hydrogen peroxide less efficiently. But solving one puzzle opened a bigger one. Hydrogen peroxide is what chemists call an oxidant. It is reactive. It loves to give up oxygen to whatever it meets. On Earth, oxidants are essential to most known forms of complex life. Our cells run on the energy released when oxidants meet fuel. Without something like hydrogen peroxide, or its cousin, oxygen gas, you cannot have animals. Europa's ocean does not have a sky to make oxygen from photosynthesis. There is no sunlight reaching the water through 20 miles of ice. But the surface keeps generating hydrogen peroxide constantly, and the chaos terrain keeps mixing surface and subsurface material together. That means oxidants from the top can get into the ocean below. If they do, then the deep ocean is not a dead pool of carbon soup. It is a chemically active environment with both fuel and oxidants. Life on Earth uses that exact combination to power itself. The implications were not lost on anyone in the room when the results came in. Europa might not just be habitable, it might be powered. Walk into any university chemistry lab and watch what happens when an experiment behaves unexpectedly. The professor stops talking. The students lean in. The instruments get checked. Because in science, when reality refuses to match your model, you do not get to argue with reality, you change the model. Europa has been doing that to chemists for 2 years now. Before Webb, the working model of Europa's surface chemistry was reasonably clean. Water ice on top, mixed with sulfur and a few other compounds dragged in from neighboring moons. Radiation processing that ice over time. A simple, almost boring chemical environment. After Webb, that picture is in pieces. There is the unexpected pattern of hydrogen peroxide. There is the carbon dioxide where none was supposed to survive. There is the table salt concentrated in the wrong region. There is also a new wrinkle that the team described almost in disbelief. They found evidence of crystalline carbon dioxide, frozen in an ordered way, alongside amorphous carbon dioxide, frozen in a disordered jumble. The same molecule appearing in 2 different forms in the same spot. That should not happen easily. Crystalline forms typically need stable conditions and time to organize. Amorphous forms typically need rapid freezing and chaos. Finding both side by side suggests the chemistry is being delivered to the surface in multiple ways, possibly over multiple time periods, and frozen under different conditions each time. Europa is not making a single batch of chemicals. It is making a stew, stirring it, adding to it, refreezing it, and serving up the result. This matters because every assumption built on the old simple chemistry needs to be revisited. Models of how long the ice has been there. Models of how often material exchanges between the ocean and the surface. Models of how much carbon the ocean actually contains. They all wobble when the surface turns out to be this complicated. There is one more piece, and it is the one Richard Cartwright kept coming back to in interviews. The chaos region is not just chemically diverse. It is chemically diverse in ways that resemble Earth. Sodium chloride and carbon dioxide and hydrogen peroxide together, in similar proportions to certain Earth environments, is not the obvious outcome you would expect from a random icy moon. The chemistry has parallels, imperfect parallels, but parallels. Think of it this way. If you stumbled across a deserted house and found a working oven, a stocked refrigerator, and a half-cooked meal on the counter, you would not assume nobody lived there. You would assume something is happening, even if you cannot see who. Europa's surface is the half-cooked meal. We did not put it there. The ocean did. And the ocean's recipe is more sophisticated than we expected. Some scientists, off the record, have started using the phrase strange chemistry without irony. They mean it literally. The chemistry is strange. It does not match the predictions. It points to something dynamic happening below. Now, strange chemistry can have many causes. It could be hydrothermal vents at the seafloor cooking up exotic compounds, the way Earth's deep ocean does around its volcanic ridges. It could be unusual mineral interactions with the rocky mantle. It could, in the most cautious phrasing scientists will allow, be biology. We do not know. We will not know until we get there. But Webb has narrowed the list of possible explanations down from many to few, and every remaining possibility is interesting. Most people picture ice as something that just sits there, cold, solid, unchanging. A frozen pond does not rearrange itself overnight. Glaciers move, but slowly, over centuries. Europa's ice does not work that way. Webb has shown us that its surface is rewriting itself faster than anyone thought possible, and the proof is hidden in two kinds of ice that should not be coexisting. There is amorphous ice, which is ice where the water molecules are frozen in a chaotic jumble. No order, no pattern. This is what radiation does to ice over time. When Jupiter's particles slam into Europa's surface, they knock the molecules out of alignment and freeze them in disarray. Given enough time, the entire surface should be amorphous ice. That was the prediction. Then there is crystalline ice, where the water molecules lock into a neat, repeating pattern. This is normal ice, the kind you get in your freezer. To make crystalline ice on Europa, you need warmth or some other process that lets the molecules rearrange themselves into order before the radiation can scramble them again. On a moon that gets pounded by Jupiter's particles every second, crystalline ice should not last. Webb saw both, side by side, in the same regions. A team led by Ujjwal Raut at the Southwest Research Institute reported this in 2025. They were not looking for it. They were studying the surface chemistry, and the spectral data kept showing crystalline ice signatures in places where, by all logic, there should only be amorphous ice. They checked, they rechecked. The crystalline ice was real. The implication is uncomfortable. The surface of Europa cannot be old and stable. If it were, radiation would have ground all the crystalline ice into amorphous mush long ago. The presence of crystalline ice means something is constantly renewing the surface. Something is bringing fresh, warm, ordered water up from below. Or something is heating the existing ice enough to let it reorganize. Either way, Europa is not frozen in time. Europa is alive in the geological sense. Picture it this way. Imagine you are walking on a beach and the sand is wet. You know it is wet because the tide just came in. If you came back 12 hours later and the sand was still wet, you would assume the tide had been there again. You would not assume it never dried out. The crystalline ice on Europa is the wet sand. The tide is whatever is reworking the surface from below. The team also noted that the porous, fractured texture of the surface in the chaos region helps explain the chemistry. A porous, warm enough surface allows the ice to recrystallize quickly. It is not solid bedrock. It is more like a sponge with chemistry seeping through it. Now stack this on top of everything else. Carbon coming up, salt coming up, hydrogen peroxide pooling in the wrong places. And now, the very ice itself is being remade. Europa is not a sealed vault. It is a system in motion, exchanging material between its hidden interior and its bright exposed shell on a regular basis. That means a probe could, in principle, sample the ocean without drilling all the way through the ice. It could land on chaos terrain and scoop up surface material that came from below recently. Europa Clipper, the spacecraft now on its way to Jupiter, is designed to do exactly that, by sniffing the moon's thin atmosphere during flybys. But before we follow that mission, there is one more puzzle Webb left behind, hidden in what it did not see. When you imagine an ice shell, you probably picture something like a hockey ring. Solid, smooth on the surface, hard if you fall on it. 20 miles of ice should feel impenetrable. Europa's ice does not behave like that. Webb's data, combined with later observations from the Juno spacecraft, has shown that the shell is something far stranger. It is porous. It is fractured. It is, in some places, more like a frozen sponge than a frozen wall. Richard Cartwright described the surface in the chaos regions as fairly porous and warm enough in some areas to allow the ice to recrystallize rapidly. That is a scientist's polite way of saying the lid is not perfectly sealed. It has tiny gaps. It has cracks running deep into the ice. It has voids and pockets and pathways that we cannot fully map yet. A study published in 2025 by a team using the Juno spacecraft's microwave radiometer provided more detail. They estimated that Europa's ice shell is roughly 18 miles thick on average, give or take 6 miles. That is consistent with earlier estimates. But the radiometer also picked up something else. Scattering. Lots of it. The microwaves were bouncing off small features inside the ice, hundreds of feet below the surface. Features smaller than a few centimeters across. What does that mean in plain language? It means the upper layers of Europa's ice are riddled with tiny pores, cracks, or bubbles. Not big highways for water to flow through, but countless small irregularities. The ice is not a uniform block. It is a textured, complicated material full of internal structure. There is a downside. The Juno team also concluded that these tiny features alone are probably too small and too shallow to act as full pathways between the surface and the ocean miles below. So microbes from the deep ocean probably cannot just swim up through the cracks. The shell is still a serious barrier, but the shell is also dynamic. Even if small cracks do not connect all the way to the ocean, the chaos terrains show evidence of much bigger disruptions. Whole blocks of ice the size of cities have been broken, rotated, and refrozen. That kind of disruption almost certainly does reach down to the ocean below. And when it does, water from the ocean can squeeze up, freeze near the surface, and leave behind the chemistry Webb is detecting. Imagine a frozen pond covered with thin spots and broken patches. Most of the ice is solid, but in certain regions, the water below has cracked through, mixed with the ice, refrozen, and left behind a stained patch. Now scale that pond up to the size of a moon and let the process repeat for billions of years. That is Europa. The implications for finding life are enormous. If Europa's shell were a perfectly sealed barrier, there would be no way for chemistry or organisms to be sampled from outside. We would have to drill, but because the shell breathes, slowly and clumsily, material from the deep ocean has been making its way up the entire time. A spacecraft does not have to dig miles down. It just has to land on the right spot and sample what is already there. That changes the entire strategy for finding life on Europa, from an impossible engineering challenge to something we can attempt within the next decade. But Webb also gave us a clue by what it failed to see. For years, one of the most exciting stories about Europa was that it might have geysers, towering plumes of water vapor shooting up from cracks in the ice, possibly tall enough to be sampled by a passing spacecraft. The image was almost cinematic, a frozen moon with fountains erupting from its surface. The story started with Hubble. In 2013, Hubble appeared to detect a plume of water vapor near Europa's south pole. In 2016 and 2017, more tentative detections came in. Each one was faint. Each one was at the edge of what Hubble could see. But each one fueled the theory that Europa was actively venting its ocean into space, the way Saturn's moon Enceladus famously does. If that were true, it would be a game changer. A spacecraft would not need to land. It could just fly through the plume and analyze the contents. Direct ocean samples, delivered for free. When Webb pointed at Europa, the team specifically looked for plumes. They had the most sensitive infrared instruments ever flown. Water vapor has a clear infrared signature. If a plume was active when Webb was watching, Webb would have seen it. It did not. Webb saw nothing. No plume signal. The team led by Geronimo Villanueva had to set what scientists call an upper limit. An upper limit is a polite way of saying, whatever might be there, it is not bigger than this. The upper limit was small. If plumes are erupting, they are weaker than expected, or they are not happening all the time. Heidi Hamel of the Association of Universities for Research in Astronomy was careful with her wording. She said the team could only confirm one thing with full confidence. They did not detect a plume during the observation. She also said that plumes might be variable. Maybe they erupt only at certain times, when Europa is at a specific point in its orbit and Jupiter's gravity stretches the Moon hardest. That qualification matters. Plumes might exist and just not have been active that day. Like a geyser on Earth that erupts every few hours, you have to be watching at the right moment. But the absence is still significant. It tells us Europa is not Enceladus. Enceladus erupts constantly. Its plumes have been seen by Hubble, by the Cassini spacecraft, by ground-based telescopes, and by Webb. They are obvious. They are huge. Europa's plumes, if they exist, are quiet by comparison. Maybe rare, maybe small, maybe non-existent. That changes the mission plan for Europa Clipper. The spacecraft was designed partly to fly through plumes if they showed up. Now, the team is preparing for the possibility that they will not get easy ocean samples from the air. Instead, Clipper will have to rely on indirect measurements, reading the chemistry of the thin atmosphere, mapping the chaos terrains, studying the magnetic field for ocean information. In a way, the missing plumes are a quiet horror story. The ocean is there, the carbon is there, the salt is there, the chemistry is rewriting itself. And yet, Europa is sealing the evidence so tightly that the most obvious door to its interior, the one Enceladus left wide open, may not exist here at all. We will have to work harder for the truth. And there is a reason the work is hard. Step into a room with a single chest X-ray machine running, and a doctor will tell you to leave. Now imagine that machine running, constantly, all over a moon. That is what Europa lives inside. Jupiter is the largest planet in our solar system. It is also surrounded by the most intense radiation belt of any object near Earth. Charged particles, mostly electrons and protons, get trapped in Jupiter's magnetic field and accelerated to nearly the speed of light. They form a deadly halo around the planet. Europa orbits inside that halo. The radiation dose at Europa's surface is roughly 500 rem per day. For comparison, the lethal dose for a human is about 500 rem total. So, an unshielded astronaut on Europa would absorb a fatal dose every single day. Within 20 minutes of stepping outside, they would already be in serious medical trouble. Within a day, they would be dead. That is not the worst of it. The radiation is not just bad for living things. It is bad for chemistry. It tears apart molecules. It scrambles signals. It destroys biological signatures within meters of the surface. If you wanted to find traces of life on Europa, the top few feet of ice would be the worst place to look. Anything there has been radiation cooked into mush. But there is a twist, and Webb showed us this clearly. The same radiation that destroys also creates. When Jupiter's particles hit Europa's water ice, they split water molecules apart. Some of those fragments recombine into hydrogen peroxide, some into oxygen gas, some into other oxidants. The surface is constantly being chemically rebuilt, just not in ways favorable to most living things. This creates the strangest possible setup for an ocean world. The top of the ice is a chemistry factory generating oxidants. The bottom of the ice is a possible habitat for life. The middle is a question. Does anything connect the two? If oxidants from the top can be transported down to the ocean, then the ocean has access to chemical energy that could power complex biology. If they cannot, then the ocean is on its own, relying only on whatever the rocky seafloor provides. The chaos terrain is the bridge. When the ice cracks and reforms in regions like Terra Regio, surface material can get folded down. Subsurface material can get pushed up. Over millions of years, even slow exchange adds up. The radiation belt above is hostile, but it is also feeding the ocean below. Picture a sealed jar of seawater buried under a battered shield. The shield is being scorched by an industrial torch from one side. The heat changes the shield's chemistry, producing useful compounds. Some of those compounds get pressed through tiny holes into the jar over time. The water inside the jar is protected from the torch, but it slowly receives the chemistry the torch creates. That is Europa, a protected ocean under a battered, chemically rich, slowly leaking shield. This is also why scientists are so cautious about predicting life there. Radiation could have sterilized the upper ice completely. Anything we find at the surface might be dead chemistry, billions of years removed from any biology. To get the real answer, you have to either dig down through the shield or wait for the ocean to push something up that has not yet been radiation blasted. Both approaches are difficult, but the second is what Europa Clipper is built for. And the ocean Clipper is trying to reach has one more strange property, hidden in how it gets its energy. Most moons in the solar system are dead. They froze billions of years ago, and they have stayed that way. They have no internal heat. They have no oceans. They have no geology that does anything interesting. Europa is different. Europa has a furnace. The furnace runs on gravity, and the gravity comes from Jupiter. Picture a stress ball in your hand. Squeeze it. It heats up a little. Now let it relax. Now squeeze it again. Do this constantly for billions of years, and the ball will be warm forever. The energy comes from the squeezing, not from anywhere inside the ball itself. That is what happens to Europa on a planetary scale. Europa orbits Jupiter in a slightly stretched, oval-shaped path. Sometimes it is closer to Jupiter, sometimes farther. When it is closer, Jupiter's gravity pulls more strongly on the near side than the far side, stretching Europa into a slightly oval shape. When Europa moves farther away, the stretching relaxes. The whole moon flexes, every orbit, every few days. This flexing is called tidal heating. On Earth, the moon's gravity does the same thing to us, only weakly. It raises ocean tides and contributes a little heat to the planet. On Europa, Jupiter's gravity is so much stronger, and Europa is so much closer to it that the flexing dumps an enormous amount of energy into the moon's interior. That energy turns into heat. The heat melts the deeper layers of ice. The melted layers form the ocean. Without Jupiter's tides, Europa would be a dead frozen rock. With them, it has a liquid ocean, a warm, rocky mantle, and quite possibly hydrothermal activity at the seafloor. The whole habitability story rests on this single mechanism. But the heat is not constant everywhere. The flexing distributes it unevenly. Some parts of the interior get more energy than others. Some regions of the ice shell get warmer than others. And those warm regions are exactly where the chaos terrain forms, where the ice cracks, melts, and refreezes in jumbled patterns. Terra Regio, the chaos region Webb scanned in detail, is almost certainly a place where tidal heating from below is concentrated. The ice there is thinner. The chemistry leaks up more easily. Webb did not just photograph a random patch of moon. It photographed a hot spot driven by Jupiter's gravity. Now here is what makes this terrifying in the cosmic sense. The same mechanism that powers Europa also powers Io, the moon next door. On Io, the tidal heating is so intense it has melted the entire interior. Io is the most volcanically active body in the solar system. Hundreds of volcanoes erupt constantly. The surface is yellow, orange, and black with sulfur and lava. Europa is just far enough from Jupiter and just thick enough with ice that the heating produces water instead of lava. A little closer in, a little less ice, and Europa could be another Io. A little farther out, a little more ice, and Europa would be a dead snowball like the moons of Saturn. Europa sits exactly on the edge. It is the rarest possible setup in the solar system, a water world held in chemical activity by the squeeze of the largest planet. If Jupiter were not there, Europa would not be. If Europa were a little different, the ocean would not exist. This is the cosmic luck that puts a possibly inhabited world in our backyard. And at the bottom of that ocean, the most interesting place of all might be waiting. 60 miles below the surface of Europa, past the ice, past the ocean's depths, there is a rocky seafloor. We have never seen it. No spacecraft has measured it directly. Everything we know about it is inferred from the moon's mass, its density, and its magnetic response. But what we do know is enough to make the seafloor the most interesting real estate in the outer solar system. Europa's interior is rocky beneath the ocean. That rock is heated by tidal forces, the same Jupiter squeezing mechanism that keeps the ocean liquid. The combination of warm rock, salty water, and constant mechanical stress is the recipe for hydrothermal vents. On Earth, hydrothermal vents are some of the most extreme and fascinating environments we have. They sit on the deep ocean floor, where volcanic activity heats the rock. Cold seawater seeps into the rock, gets heated, dissolves minerals from the surrounding stone, and then erupts back into the ocean as scalding, mineral-rich plumes. Around these vents, life thrives. Bacteria, tube worms, strange shrimp, an entire food web built without sunlight, powered by chemistry alone. When biologists first discovered Earth's vents in 1977, the find rewrote what we thought life needed. Before that, every known ecosystem on Earth depended ultimately on sunlight. Plants captured sunlight. Animals ate plants. Predators ate animals. The vent ecosystems destroyed that rule. They proved life could be built on chemistry alone, on minerals dissolved from rock, on the energy released when seawater met scalding stone. Many origin of life researchers now believe Earth's life may have started at such vents. The deep ocean floor, 4 billion years ago, was a chemistry laboratory running endless experiments. One of those experiments produced something that could copy itself. From that single accident, every cell on Earth descended. Now turn that idea to Europa. Europa has the same ingredients: rocky seafloor, tidal heating, salty water. There is no sunlight, but the vent ecosystems on Earth do not need sunlight. They need chemistry. Europa has chemistry. Webb just confirmed that. The question is whether Europa actually has working vents right now. The evidence is indirect. The unusual salts on the surface suggest the ocean has been chemically processed in a way consistent with vent activity. The carbon dioxide signature matches what you would expect from rock-water reactions deep down. The whole pattern is the kind of fingerprint hydrothermal activity would leave. Picture the seafloor, total darkness, pressure so high that on Earth it would crush a submarine, temperature swinging from near freezing in the open water to several hundred degrees at the vent mouths, mineral chimneys rising tens of feet, belching black mineral-rich water. Around the chimneys, if Europa is like Earth, mats of microbial life feeding on the chemistry. Each microbe a tiny machine running on sulfur, hydrogen, or carbon, harvesting energy from the meeting of hot rock and cold water. We cannot confirm any of that yet. We can only say that the upstairs chemistry is consistent with the downstairs being active. Webb cannot see the seafloor. Webb can only read the leakage at the top. But the leakage is suggestive, strongly suggestive, enough that NASA and the European Space Agency are sending 2 separate missions to find out more, missions that took decades to plan and billions of dollars to build. If hydrothermal vents are running down there, then Europa is not just habitable. Europa is, at a minimum, exactly the kind of place where Earth's life almost certainly started. That parallel is impossible to ignore. Imagine the early Earth, 4 billion years ago. The surface is hostile. Volcanoes erupt constantly. The atmosphere is poisonous. Meteorites still pound the planet. There is no oxygen worth breathing. No plants. No soil. The sky is dim because the young sun is fainter than it is today. But down at the bottom of the early oceans, on the rocky seafloor, near hydrothermal vents, something is different. The water is warm. The chemistry is rich. The conditions are stable for a long time. Trillions of natural experiments are running, every second, on every vent, on every ocean ridge. And after some unknown stretch of time, one of those experiments produces a molecule that can copy itself. That molecule is the ancestor of every living cell on Earth. From it came bacteria, then more complex single cells, then multicellular life, then plants and animals and us. The entire tree of life on this planet, possibly, starts at a vent. This story is not proven. but it is the leading theory among origin of life researchers. Several lines of evidence support it. The chemistry of vents naturally produces the precursors to life. Vents provide both energy and protected environments. The oldest fossils on Earth, billions of years old, look chemically similar to bacteria that still live near modern vents. Now compare that early Earth to Europa today. Europa has a salty ocean. Earth had a salty ocean. Europa has a rocky seafloor. Earth had a rocky seafloor. Europa has tidal heating from Jupiter. Early Earth had radioactive heating from its own interior. Europa has carbon and salts and oxidants. Early Earth had carbon and salts and oxidants. Europa is protected from harsh surface conditions by a thick ice shell. Early Earth's vent ecosystems were protected by miles of seawater above them. The ingredients are not just similar, they are nearly identical. The only difference that matters is time. Earth has had 4 billion years for its experiment to produce a result. Europa has had roughly the same. If the cradle of life on Earth was a hydrothermal vent under a deep, dark ocean, then the cradle of possible life on Europa is sitting right now under 60 miles of water and 20 miles of ice. The same cradle, the same chemistry, the same energy, just a different sky overhead. This is what makes the Webb findings hit harder than any previous Europa discovery. Webb did not just confirm that water and chemistry are there. Webb confirmed that the chemistry pattern looks like the kind of activity that, on Earth, eventually produced us. Now, think about what this means for the universe. If life can start independently in two places in the same solar system, then life is not a freak accident. It is a natural outcome whenever the right conditions appear. The Milky Way alone has hundreds of billions of stars. Many of them have moons or planets with hidden oceans. Europa is just the closest case of those conditions. If it has life, then countless other worlds out there probably do too. If Europa is dead, then we will have to think hard about why. Same chemistry as Earth, same energy, same time, and no result. That would mean something specific about Earth is special. We do not know what that something would be. It would be a deeply unsettling answer. Either way, Europa now sits in the middle of one of the biggest questions humans have ever asked. Are we alone or not? And the answer is closer than it has ever been. To get to the ocean, you have to get through the ice. So how thick is the ice? For decades, scientists have argued about this. The estimates range wildly. Some studies put the ice shell at 3 miles thick. Others put it at 25 miles or more. The disagreement is not just academic. It changes everything about whether we can ever reach the ocean. A 3-mile shell is, in principle, drillable. We have drilled deeper into Earth in some places. A spacecraft equipped with a melt probe, a heated probe that slowly sinks through ice, could, in theory, melt its way through 3 miles in a few years. A 25-mile shell is a different beast. That is far beyond anything humans have engineered. The pressure would crush ordinary probes. The temperature gradient would be enormous. The mechanical challenges of drilling that deep in remote operation in a radiation environment with no possibility of human repair are staggering. So which is it, thin or thick? Webb did not answer this directly because Webb cannot see through ice. But 2 other lines of evidence have narrowed the question down. The first comes from the chaos terrains. The very existence of regions like Terra Regio, where the ice is broken and rearranged, suggests the shell is not uniformly thick. There are thinner spots. There are thicker spots. The breakage requires either local melting or local stress, both of which work better in thinner regions of the shell. The second comes from the Juno spacecraft, which performed close flybys of Europa in 2022 and 2024. Its microwave radiometer measured the temperature profile through the upper ice. The team, led by Stephen Levin at NASA's Jet Propulsion Laboratory, published their results in late 2025. They concluded the ice shell is about 18 miles thick on average, give or take 6 miles. That is in the middle of the older range, thicker than the optimists hoped. thinner than the pessimists feared. 18 miles. That is a long way. To put it in perspective, 18 miles is about the distance from one side of a major city like Chicago to the other. Imagine drilling straight down through that much ice, in temperatures of 300 degrees below zero, on a moon nearly 500 million miles from Earth, with no chance of sending help if something goes wrong. That is what reaching Europa's ocean would actually require. For now, no mission is being seriously planned to do it. Europa Clipper, the spacecraft already on its way, is not a lander, it is a flyby probe. It will swing past Europa dozens of times, scanning the surface and atmosphere, but it will not touch down. A later mission, the Europa lander, has been studied but not funded. It would land on the surface and dig a few inches, maybe a few feet, into the ice. Not 18 miles. So, how do we ever sample the ocean directly? The answer goes back to the chaos terrain. In places where the ice has been broken and rearranged recently, ocean material has been brought up close to the surface. A lander could touch down in chaos terrain, scoop a few feet of ice, and effectively sample ocean chemistry from billions of years of leakage. That is the strategy, not to drill through the wall, to find the cracks where the wall is leaking and read the spillage. Webb just told us where to look. While Webb was reading the chemistry on Europa's surface, another spacecraft was listening to the ice itself. Juno, the workhorse Jupiter probe that has been orbiting the giant planet since 2016, made 2 close flybys of Europa. The first was in September of 2022. The second was in late 2024. Juno was not designed primarily for Europa work. It was built to study Jupiter's interior, but its instruments, including a microwave radiometer, turned out to be incredibly useful for peering into Europa's ice as well. The microwave radiometer is exactly what it sounds like, an instrument that picks up the natural microwave emission of an object. Different materials, at different temperatures, emit different microwaves. By reading those signals carefully, you can map out the temperature and structure of the upper layers of a moon's surface. When Juno swept past Europa, the radiometer picked up signals that came not just from the very top, but from up to hundreds of feet below the surface. Microwaves can penetrate ice that infrared and visible light cannot. The team that analyzed the data, led by Stephen Levin at NASA's Jet Propulsion Laboratory, published their findings in the journal Nature Astronomy in December of 2025. What they found added a crucial dimension to Webb's story. The ice shell is roughly 18 miles thick on average, with significant uncertainty. But more importantly, the upper ice is full of small scattering features, microwaves bouncing off countless tiny irregularities, pores, bubbles, cracks, none of them large by themselves, but together they paint a picture of an ice shell that is structurally complicated. To picture the difference, imagine 2 blocks of frozen water. One is clear, smooth, like the ice in a fancy whiskey glass. The other is cloudy, full of tiny air bubbles and stress lines, like the ice that forms in a freezer over time. Juno's reading suggests Europa's upper ice is much closer to the cloudy version. The shell is not a clean window. It is a textured, fractured material full of internal structure. This matters for 2 reasons. First, it explains how Webb's chemistry findings make sense. A porous, fractured upper ice gives material from below more pathways to reach the surface. Carbon dioxide, salt, hydrogen peroxide. All of them have an easier time arriving at the top if the ice is not perfectly solid. Second, it tells us something about the history of the shell. Pores and cracks at those depths suggest the upper ice has been through significant stress. Either repeated cycles of freezing and refreezing, or sustained tidal flexing, or both. The shell is not a static structure. It is a worked material, like leather that has been bent and folded many times. The Juno team noted that these small features are probably too small to act as channels for large-scale ocean-to-surface transport. Microbes cannot just swim up through them, but for chemistry, the picture is different. Gases and dissolved compounds can migrate through tiny pathways over geological time. even if larger organisms cannot. So between Webb and Juno, we now have a coherent picture. Webb tells us what is leaking out. Juno tells us how the leaking happens. Together, they describe an icy moon that is in slow geological motion, mixing its insides with its outside, not violently, like Enceladus with its plumes, but constantly, steadily, for billions of years. The picture is no longer of a frozen vault. It is of a quietly breathing world, exchanging gases and salts and carbon between its hidden ocean and its starlit shell. Every century, every millennium, and every breath, if we are reading it right, hints at something below that might be alive. If Terra Regio is the most chemically interesting place on Europa, Connemara Chaos is the most visually disturbing. The first time scientists saw clear images of Connemara, taken by the Galileo spacecraft in the late 1990s, the response was confusion. Astronomers expected ice. They got something that looked like a frozen shipwreck. Picture a region the size of Massachusetts. The surface is broken into dozens of flat slabs of ice, each one a few miles across. The slabs are not aligned. They are tilted, rotated, shoved against one another, and sometimes turned completely around compared to their neighbors. Between them lies a darker, lumpy material that looks like it once flowed, then froze in place. The simplest explanation is this. At some point in the geological past, the ice in this region softened or melted from below. The solid upper layer broke into pieces. The pieces floated on a slushy or liquid layer for a while, drifted, rotated, and then refroze in their new positions. Like icebergs in slush, only the slush eventually hardened back into the surrounding ice. For that to happen, the ice shell beneath Connemara had to weaken catastrophically. Either the ocean rose up locally, melting the underside of the ice, or warm material from the mantle, transmitted through the ocean, heated a specific spot until the upper crust gave way. Either explanation requires real heat, real movement, real activity, not just slow drift. Connemara is dated, by counting impact craters on its surface, to be young by Europa standards, possibly only a few tens of millions of years old. In a moon that is 4.5 billion years old, that is fresh. We might be looking at a feature that formed when dinosaurs were still walking the Earth. Now combine that with Webb's chemistry findings at Terra Regio and other chaos regions. The chemistry is fresh, the geology is fresh. The whole pattern points to a moon where chaos events keep happening, not constantly, not violently, but on a geological clock that has not run down. Some scientists have proposed that chaos terrains form when warm blobs of ice rise through the shell, like wax in a lava lamp. The blobs push up from below, melt, and rearrange the surface above them, and then sink back down once they have given up their heat. Each chaos region is a frozen record of one of these blobs reaching the upper ice. Others have proposed that chaos forms when the ocean directly breaks through, in events that briefly connect the deep water to the surface. Those events would be the most exciting of all, because they would mean ocean material was thrown directly onto the surface, where probes could sample it. The truth is, we do not know which model is correct. Both fit different pieces of the data. Probably some combination of both is happening. But here is what should not be lost. Every chaos region on Europa is a place where the ice shell has been disrupted from below. Every chaos region is therefore a place where ocean chemistry has reached the upper ice in the geological recent past. There are dozens of chaos regions on Europa. Each one is a potential sampling site for the ocean. If you were sending a probe to look for signs of life, you would not pick a smooth, flat plain. You would pick a chaos region. You would pick the place where the underground laboratory has spilled its experiments onto the floor above. Europa has marked the spots for us. The map is already drawn in ice, and the next feature, Webb examined, hints at how the marking happens. If you look at images of Europa from any angle, you see long parallel lines stretched across the surface, thousands of them. Some are dark, some are light, some run for hundreds of miles in straight or gently curving paths. They are called double ridges, because they almost always appear as pairs of parallel walls with a valley between them. Double ridges are everywhere on Europa. They are the most common geological feature on the Moon, and nobody fully understands how they form. Picture two long parallel walls of ice, each about 100 yards tall, running for hundreds of miles across a flat plain. The walls are roughly the same height. The valley between them is consistently the same width. They look like train tracks made of ice. Several theories have been proposed. One says they form when a deep crack opens, and ocean water rises up through the crack, then freezes at the edges, building up parallel walls over time as the crack opens and closes with tidal flexing. Another says they form when the ice shell bends along a fault line, pushing up matching ridges on either side. A third says they are the surface signature of small pockets of liquid water trapped within the ice, which freeze and expand, cracking the surface above them in a predictable double-walled pattern. In 2022, a study led by researchers at Stanford University looked at a similar feature in Greenland. Greenland's ice sheet has occasionally produced small double ridges of its own, and we can study those directly. The Greenland ridges appear to form when shallow water pockets within the ice freeze and force the surface upward in pairs of matching peaks. If the same process happens on Europa, it would mean Europa's ice shell contains lakes within it, shallow pockets of liquid water trapped between the ocean below and the icy surface above. If those internal lakes exist, they change the habitability picture. The lakes would be smaller and more accessible than the deep ocean. They would have their own chemistry, their own conditions. They could even be habitable in their own right, separately from the main ocean. Webb does not have the resolution to see individual ridges or lakes, but Webb's chemistry findings, combined with the ridge mystery, suggest a coherent picture. Europa's ice shell is not just one thing. It has structure. It has internal water pockets. It has cracks that connect different layers. It has chaos regions where everything is mixed. Now picture standing on Europa and walking across one of these ridges. The ground would feel slightly raised. To your left, a long parallel wall of ice. To your right, another wall. Between them, a valley a few hundred feet wide. Above you, a black sky with the enormous bulk of Jupiter dominating one whole quarter of it. Beneath your boots, somewhere, ice that contains the imprint of whatever process built this strange feature hundreds of thousands or millions of years ago. The ridges are the geological diary of Europa. They record the Moon's history in lines across its face. Each one is a chapter in how the ice has flexed, cracked, and re-healed over billions of years. Reading them is one of the main goals of the upcoming Europa Clipper mission, which will photograph them in much higher detail than anything we have today. If the ridges turn out to mark places where water has been close to the surface, then they double the number of sampling sites available to future missions. Chaos terrains plus ridges, tens of thousands of potential windows into Europa's interior, and in some places, the windows are circular instead of linear. Scattered across Europa are small, roughly circular features called lenticulae. The name comes from the Latin word for lentil, because that is what they look like from orbit. Small, flat, oval blobs on the surface, ranging from a few miles to a few dozen miles across. Some lenticulae are domes. They bulge upward, like blisters in the ice. Others are pits, sunken below the surrounding surface. Still others are flat-topped patches that look like they have been smoothed over, with no obvious connection to the terrain around them. Lenticulae are not as eye-catching as chaos regions or double ridges. They are subtle, but they are widespread, and they may be the clearest signature of warm material rising through the ice from below. The leading theory says lenticulae form when blobs of warmer, softer ice rise through the colder upper shell. Picture a pot of thick porridge with bubbles rising slowly to the top. Each bubble that breaks the surface leaves a small disturbance. The lenticulae are those disturbances, frozen in place when the rising blob loses its heat and stops moving. For this to work, Europa's ice shell has to have convection. Convection is the slow circulation of material driven by heat. Hot material rises, cool material sinks, and the whole system slowly cycles. On Earth, the mantle convects this way over millions of years, driving plate tectonics. On Europa, the ice shell may convect on similar timescales, with warm, soft ice rising and cold, brittle ice sinking. If lenticulae are convection signatures, then Europa's ice shell is alive in a way that ordinary frozen lakes are not. It is being constantly rebuilt from within. Material from deep in the shell, near the ocean, is being slowly carried to the surface. Material from the surface, exposed to radiation and chemistry, is being carried down. The shell is a slow conveyor belt that has enormous implications for the habitability picture. If material at the surface is eventually buried deep within the shell, then the oxidants generated by radiation are not stuck at the top. They are being transported, however slowly, toward the ocean. The same hydrogen peroxide and oxygen that Webb's data suggests is forming at the surface could be making its way into the ocean over millions of years. Once there, it would provide chemical energy for any life that might exist below. This is the missing link that life on Europa would need. Without it, the ocean is closed off from any energy source except hydrothermal vents at the seafloor. With it, the ocean has access to both vent energy from below and oxidant energy from above. That doubles the possible metabolic pathways. It also means Europa might be more habitable than Earth's deep oceans, which only get oxidants from the surface through slow mixing. We do not yet have direct proof that convection is happening. The lenticulae are suggestive. Models support the idea, but until we get high-resolution images of how lenticulae are forming now, the convection story is theory, not fact. Europa Clipper is being specifically designed to test this. Its ice-penetrating radar will image the inside of the upper shell. If convection is happening, the radar should show layers of warm and cold ice, traces of rising blobs frozen at different depths. If the shell is dead and static, the radar will show uniform ice. The answer will land in the next decade. We are not waiting forever. And what we have already seen at the surface tells us the answer cannot be that nothing is happening. Earlier we touched on the discovery of crystalline and amorphous ice on Europa's surface. Now, let us look at why this finding is so deeply strange that it forced scientists to rewrite their basic models. Amorphous ice forms when water freezes too fast or under too much radiation for the molecules to organize. The water molecules end up in a jumbled, disordered arrangement, like a crowd of people frozen in mid-stampede. Amorphous ice is the natural product of radiation damage. On any icy moon bathed in radiation, you expect to find lots of it. Crystalline ice forms when water freezes slowly, or when amorphous ice is warmed up enough that the molecules can rearrange themselves into a neat repeating pattern, like a crowd of people who have had time to line up in orderly rows. Crystalline ice is what you find on Earth, where conditions are mild and stable. The problem on Europa is that crystalline ice and amorphous ice have very different stability properties. In the radiation environment near Europa's surface, amorphous ice should be the only kind that lasts. Crystalline ice should be quickly bombarded into disorder by Jupiter's particles, becoming amorphous within thousands or tens of thousands of years. Webb saw both. In the same regions, in significant quantities. The team that reported this, led by Ujjwal Raut at the Southwest Research Institute, had to grapple with what it meant. The crystalline ice could not have been sitting on the surface for long. It would have been radiation damaged by now. So it had to be recent, very recent, continuously refreshed. That refreshment can happen in only a few ways. Either the surface is being warmed periodically, perhaps by tidal flexing concentrated in chaos regions, allowing the ice to recrystallize before radiation can fully disorganize it. Or fresh water is being delivered to the surface from below, freezing into crystalline ice as it sits in the slightly warmer environment of the chaos terrains. Or both. Most likely both. Both processes feed the same picture. Europa's surface is not a static record of ancient ice. It is being constantly refreshed by activity from below. There is a deeper implication. The surface ice we are looking at on Europa is geologically young, possibly only millions or tens of millions of years old in many places. Compared to the Moon's 4.5 billion year age, that is yesterday, the Europa we see today is not the Europa of the distant past. The surface keeps getting wiped clean and rewritten. That is a horror story for some scientists and a gift for others. A horror story because it means any signature of ancient biology, if it ever existed at the surface, would have been erased long ago. A gift because it means whatever we sample today is fresh. We are not reading ancient fossil chemistry. We are reading what the ocean is doing right now, or at least within the last few million years. For astrobiologists, this is the better outcome. Trying to detect billion-year-old biosignatures is much harder than detecting active chemistry. Fresh material means a higher chance of finding intact organic compounds, intact cellular structures if any exist, and intact chemical fingerprints of any biological activity below. Europa's habit of erasing its old face is, paradoxically, what makes it readable. The chemistry on the surface today is a real-time report from the ocean below. That report includes one more strange detail Webb caught, a clue hidden in the carbon itself. Carbon comes in different versions. Almost all the carbon in the universe is carbon-12, with 6 protons and 6 neutrons. A small fraction is carbon-13, with 1 extra neutron. The two versions behave almost identically in chemistry, but not exactly. Different processes prefer different versions in subtle ways. This subtle preference is one of the most powerful tools in chemistry. By measuring the ratio of carbon-12 to carbon-13 in a sample, you can often tell where the carbon came from. Comets and asteroids have one ratio, Earth's mantle has another. Living organisms have yet another. The ratio acts like a fingerprint, identifying the source. Webb measured the carbon isotope ratio of the carbon dioxide on Europa's surface. This was not the headline finding when the papers came out, but for chemists, it was one of the most important details. The ratio Webb measured was consistent with carbon that has been processed inside a planetary body. It did not match the ratio expected from interplanetary dust. It did not match the ratio expected from comets. It matched, roughly, what you would expect if the carbon came from rock-water chemistry deep inside Europa. That is a strong piece of evidence for the ocean origin theory. The isotope ratio, by itself, would not be conclusive. Combined with the geographical concentration in Terra Regio, the salts in the same region, and the recent timescale of deposition, it forms a chain of evidence that all points the same direction. The carbon came from Europa's interior, specifically from the rocky watery system inside the Moon. There is one more wrinkle. On Earth, biological processes leave a distinct isotope signature. Living things preferentially use carbon-12, leaving them slightly enriched in the lighter version compared to their environment. If life were processing carbon in Europa's ocean, and that carbon were being delivered to the surface, we might expect to see a biological isotope signature. Webb did not have the resolution to make a definitive call on this. The carbon at Terra Regio has an isotope ratio consistent with internal processing, but whether some of that processing involves biology is impossible to say from current data. We need more detailed measurements, ideally from a spacecraft landing on or flying through chaos terrain material. Europa Clipper will not land, but its mass spectrometer, called mass specs, will analyze the thin atmosphere around Europa during close flybys. That atmosphere is created when surface molecules are kicked off by Jupiter's radiation. If mass specs detects organic molecules in the atmosphere, and those molecules have isotope ratios suggesting biological processing, that would be the closest we have come to a positive sign of life on another world. This is a careful, cautious statement. No one is predicting that Clipper will detect life, but the instruments are precise enough that, if biological isotope signatures are present in Europa's atmosphere, Clipper has a real chance of seeing them. For now, The carbon isotopes on Europa tell us this much. The carbon is internal. The carbon is recent. The carbon could be the product of geology alone. It could also be the product of geology plus something else. That something else is what every astrobiologist on Earth desperately wants to know about. And the answer is closer than it has ever been. But before we get there, we have to think about what kind of life Europa could actually support. When most people think of alien life, they imagine green humanoids or maybe enormous tentacled creatures from the deep. The reality, if there is life on Europa, is almost certainly far smaller and far stranger. The most likely form of Europa life would be microbial, single-celled organisms similar to the bacteria that dominate Earth. They would live in the ocean, probably concentrated around energy sources like hydrothermal vents on the seafloor. They might form mats or films on rocks near the vents. They might float in the open water, feeding on whatever chemistry the ocean provides. These organisms would not photosynthesize. There is no sunlight at the bottom of a 20-mile ice shell. Instead, they would chemosynthesize. They would draw energy from chemical reactions, specifically from the meeting of oxidants like the hydrogen peroxide Webb detected, and reductants like the sulfur and iron compounds that hydrothermal vents probably produce. This is not exotic biology by Earth standards. We have organisms on Earth that do exactly this. They live around deep-sea vents. They live deep underground in rock. They live in toxic, acidic pools and in places that no other life can survive. They are called extremophiles, and they are everywhere we have looked for them. Europa's environment would be challenging by Earth standards, but it would not be unprecedented. If Europa life exists and resembles Earth's extremophiles, it would be tough, slow-growing, and chemically efficient. It would not need much energy. It would reproduce slowly, on geological timescales, rather than minutes or hours. It might form colonies that have lived in the same place for millions of years. Some scientists have speculated about more complex life. Could there be multicellular organisms in Europa's ocean? Worms? Fish? Even larger creatures? The honest answer is probably not. Complex life on Earth needs lots of energy, and Europa's ocean almost certainly does not have lots of energy. The chemistry from the seafloor vents and the oxidants from above are real, but they are limited. They could support a thin population of microbes. They probably could not support large active animals, but this is speculation based on Earth biology. We do not know what kinds of life might be possible in environments different from ours. It is conceivable that Europa hosts a kind of biology we have not imagined. It is also conceivable that it hosts nothing at all. The crucial point is that the conditions for life are there: water, carbon, salts, energy sources, chemical complexity, time. Whatever rules govern whether life starts in a place like this, they should be able to operate on Europa. If life is common in the universe, Europa should have it. If Europa does not have it, then life is much rarer than we hoped, and the rules for starting it must be much stricter than we currently understand. Either answer matters enormously. The presence of life on Europa would mean the universe is teeming with biology. The absence of life on Europa, given how favorable the conditions appear to be, would mean we are in a much lonelier cosmos than we thought. There is no neutral outcome here. Europa is a critical experiment in cosmic biology. The results, when we get them, will reshape how we think about everything. And the experiment is about to start. Pour lemon juice on your skin and you feel a slight sting. The juice is acidic. Now imagine an entire ocean with that kind of acidity, or worse. One of the open questions about Europa's ocean is its pH. Is it acidic, like lemon juice? Is it neutral, like distilled water? Is it alkaline, like household bleach? The answer matters enormously for whether life could survive there. Most of Earth's life evolved in seawater that is slightly alkaline. Some organisms tolerate acidity, but few thrive in very acidic conditions. If Europa's ocean is highly acidic, that would close off many possibilities. If it is roughly neutral or alkaline, the door stays wide open. The acidity depends on what is in the ocean. Webb found carbon dioxide on the surface. Carbon dioxide, when dissolved in water, makes that water more acidic. It forms carbonic acid, the same compound that makes soda fizzy and slightly tart. Lots of carbon dioxide in the ocean would mean an acidic ocean. But Webb also found sodium chloride. Sodium chloride is a neutral salt. It does not change the pH of water much by itself. However, if the ocean has interacted with rocky minerals on the seafloor, those minerals could neutralize acidity. Calcium and magnesium-rich rocks dissolve slightly in water, releasing alkaline compounds. Over billions of years, that process could buffer an ocean against acidification. Modeling Europa's pH has been a hard problem. Scientists have proposed values ranging from as low as 2.6, which would make the ocean roughly as acidic as lemon juice, to above 10, which would make it more alkaline than ammonia. The huge range reflects how little we actually know. The latest research, including studies that take Webb's findings into account, suggests the ocean is most likely in the neutral range, probably between 6 and 9 on the pH scale. Earth's oceans are around 8, so Europa's ocean might actually be similar to Earth's, chemically speaking, just much colder and much deeper. If that is right, then the acidity is not a barrier to life. The ocean would be a chemically friendly place by the standards of Earth biology. But there is a caveat, and it is an interesting one. The ocean might not have uniform acidity. Like Earth's oceans, Europa's might have layers, currents, and gradients. Near the seafloor, where vents are heating the water and releasing minerals, the chemistry might be one way. Near the underside of the ice, where surface chemistry is being delivered down, the chemistry might be another way. In between, mixing and circulation could create zones of different acidity. This means, even if part of the ocean is hostile, other parts could be perfectly habitable. The way Earth has both acidic volcanic pools and gentle ocean reefs, Europa might have a range of environments under its ice, some welcoming, some not. Life would only need to find a single welcoming zone to survive. That zone, if it exists, is almost certainly near the seafloor, where the chemistry is fresh from rock-water reactions, where the temperature is warmest, where any vent organisms would have the best chance of stable conditions. So, the acidity question is, for now, an open one. The best guess is that the ocean is moderately friendly to life as we know it, with possible variations across its depth. The worst case is that it is too acidic in parts to support biology. The best case is that it is broadly Earth-like in its basic chemistry. We will not know for sure until a spacecraft directly samples the ocean material, either through chaos terrain leakage or, eventually, through deeper exploration. And waiting in the wings, getting closer every day, is the spacecraft built to do exactly that. In October of 2024, a spacecraft the size of a basketball court lifted off from Florida and began the long journey to Jupiter. Its name is Europa Clipper. It is the most ambitious spacecraft ever built specifically to study a single moon. Clipper is enormous. Its solar panels are the largest ever flown on a planetary mission, because at Jupiter's distance, sunlight is weak. The panels stretch nearly 100 feet from tip to tip. They have to gather every available photon to power the instruments. The spacecraft will arrive at Jupiter in 2030. From there, it will spend years performing close flybys of Europa, around 50 in total. Each flyby will bring Clipper to within a few dozen miles of Europa's surface. At those distances, the instruments can map the chemistry, the geology, and the magnetic field in detail no telescope can match. Clipper carries 9 main instruments. Each one is designed to answer a specific question about Europa. There is a mass spectrometer called MassSpex that will sniff the thin atmosphere around Europa and identify any organic compounds present. There is an ice-penetrating radar that will look through the shell, mapping its structure and possibly detecting pockets of liquid water within. There is a magnetometer that will refine our knowledge of the ocean's depth and salinity through the magnetic signature it produces. There are cameras that will photograph the surface at resolutions far beyond anything we have today. There is a thermal imager that will identify warm spots, possible locations where ocean material is reaching close to the surface. There is a spectrometer that will continue the chemistry mapping Webb began, but from much closer range. The mission's primary goals are not to detect life directly. They are to determine whether Europa's ocean is habitable. To answer that, Clipper needs to confirm the ocean's existence directly through magnetic measurements, characterize the ice shell's thickness and structure, identify the chemistry of the surface and atmosphere, and look for places where ocean material is being exchanged with the surface. Webb has given Clipper a head start on the chemistry question. Clipper now arrives knowing where to look: Terra Regio, other chaos terrains. Regions where Webb has already detected the strange chemistry from the deep. There is also a remote possibility that Clipper could detect direct biosignatures. If organic compounds with biological isotope signatures are present in Europa's atmosphere, Maspex is sensitive enough to identify them. The team has been careful not to oversell this possibility. Detecting life is hard. The signatures could be ambiguous. Geological processes can produce molecules that look biological, but the chance is not zero. In a decade, we may have an answer to one of humanity's oldest questions. Are we alone in the solar system? Clipper is the closest we have ever come to asking that question, with the tools needed to answer it. The combination of Webb's pre-mission surveying and Clipper's close-up investigation is unprecedented. We have never approached a possibly inhabited world this prepared. But Clipper is not the only spacecraft on its way. Another mission from another agency is also heading toward Jupiter, and it is hunting for the same answers. While NASA was building Europa Clipper, the European Space Agency was building its own Jupiter mission. The Jupiter Icy Moons Explorer, called JUICE. It launched in April of 2023, more than a year before Clipper. JUICE will arrive at Jupiter in 2031. Its primary target is not Europa. It is Ganymede, Jupiter's largest moon, which also has a subsurface ocean. But JUICE will perform 2 flybys of Europa during its mission, and those flybys will complement Clipper's work in important ways. JUICE carries a different set of instruments than Clipper. Some overlap, some are unique to JUICE. The combination of 2 different spacecraft, with 2 different instrument suites, observing Europa from 2 different angles, is the kind of scientific redundancy that scientists love. If both missions detect the same thing, the finding is rock solid. If they disagree, the disagreement itself reveals important details about what is happening. JUICE was a different design philosophy. NASA built Clipper specifically for Europa. Europe built JUICE as a tour of multiple icy moons. JUICE will spend most of its mission at Ganymede, but its Europa flybys will use the same instruments to compare the 2 ocean worlds directly. That comparison is scientifically valuable. Ganymede and Europa both have hidden oceans, but their oceans are different. Ganymede's is much deeper, possibly hundreds of miles below the surface, and sandwiched between layers of ice. Europa's is shallower, closer to the seafloor, and possibly in direct contact with rock. By studying both moons with the same tools, JUICE will help scientists understand which ocean configuration is more likely to support life. Is it better to have a shallow ocean in contact with a rocky seafloor, like Europa, or a deeper ocean isolated between ice layers, like Ganymede, or are both habitable in different ways? For Europa specifically, JUICE will provide independent confirmation of whatever Clipper finds. If Clipper detects unusual chemistry, JUICE can verify it. If JUICE sees evidence of plume activity, Clipper can follow up. The 2 missions will overlap in time for several years, allowing real-time scientific exchange. There is one more advantage. JUICE has slightly different orbital geometry than Clipper. It will pass over different regions of Europa, possibly including the southern hemisphere areas where Hubble once tentatively detected plumes. If those plumes are real and active, JUICE might catch them when Clipper does not. Together, The two missions form a two-pronged investigation of Europa's habitability. NASA on one side, ESA on the other. Different instruments, different perspectives. The same fundamental question. This is the most coordinated international effort to investigate a possibly habitable world that humans have ever mounted. The cost, the time, and the technical difficulty are all enormous. Both agencies decided the question was worth the investment. The answer, when it comes, will be the joint work of thousands of scientists across 2 continents. It will be the fruit of decades of telescope observations, including the Webb findings that pointed the way. It will rewrite textbooks, regardless of which way it falls. And it will arrive within the lifetimes of most people watching this video. That timing matters. We are not waiting for the distant future to learn whether Europa hosts life. We are waiting a decade, maybe less if Webb keeps revealing surprises and the missions accelerate their analysis. But what exactly will we be looking for as evidence? If a spacecraft flies past Europa and detects a certain chemical in the atmosphere, how would scientists decide whether that chemical means life is there? This question, the question of what counts as a biosignature, is harder than it sounds. A biosignature is any chemical or pattern that strongly suggests biology rather than geology. The classic example is oxygen. On Earth, oxygen in the atmosphere is overwhelmingly produced by photosynthesis. If you detected lots of oxygen on another planet, you would have strong reason to suspect life. But it is not that simple. Oxygen can also be produced without biology, especially on small bodies where radiation splits water and releases the oxygen. Europa's surface, in fact, produces oxygen this way, so oxygen alone is not enough. Better biosignatures are combinations of chemicals that should not coexist without something actively producing them. On Earth, methane and oxygen are both present in the atmosphere. They react chemically with each other. If life were not constantly replacing the methane, it would disappear within a few decades. The simultaneous presence of methane and oxygen is a sign that something is actively maintaining a chemical disequilibrium. That something is life. For Europa, scientists are watching for similar disequilibrium signatures, specific organic compounds that would not survive on a dead surface, carbon isotope ratios that match biological processing rather than pure geology, patterns of chemicals that resemble Earth biology in their structures and proportions. There is also a concept called the ladder of life detection. Different levels of evidence point to different levels of confidence. At the bottom of the ladder, you have hints, strange chemistry, like what Webb has already detected. These are not biosignatures. They are reasons to look closer. In the middle of the ladder, you have specific organic molecules, amino acids, lipids, sugars. Finding these would be exciting but not conclusive, because non-biological processes can sometimes produce them too. At the top of the ladder, you have direct evidence. Cells, genetic material, fossils, anything that can only be explained by living organisms. Europa Clipper is designed to detect signals in the lower and middle parts of the ladder. It will not see cells. It cannot dig deep enough or look closely enough for that. But it can detect organic compounds and chemical patterns that would either rule out life or strongly suggest it. What would a positive result actually look like? It would probably be a report from mass specs, the mass spectrometer, identifying a complex organic compound in Europa's atmosphere with an isotope signature consistent with biological processing. That detection would not, by itself, prove life. But it would justify the next mission, which would be a lander dedicated to looking more closely. What would a negative result look like? It would be the absence of any complex organic chemistry beyond what simple geological processes can produce. Lots of water, salts, basic gases. Nothing fancy. That outcome would push the search for life further out into the solar system, toward moons like Enceladus and Titan, and beyond. Either outcome would be enormous news. Either outcome would reshape our view of the universe. There is one more possibility, and it is the most unsettling. Clipper could find evidence that strongly suggests life, but is not conclusive. Compounds that look biological, patterns that look biological, But that falls short of the standard required for confident detection. That outcome would leave us in scientific limbo. Strong hints, no proof. A demand for a follow-up mission that might not happen for another 2 decades. That limbo state might be where we end up. And it might be a horror story in its own right, because we would know that the answer is almost certainly yes, but we would not be allowed to say so. Webb has already started us down that path. The findings already point towards strange, unexplained chemistry that resembles biology in some respects. If Clipper confirms and deepens those findings without sealing them, we will be left waiting longer than anyone wants. But before that happens, Webb is going to keep looking. The Webb observations of Europa we have discussed so far were made early in the telescope's mission. They were short, they were exploratory, they used only a few minutes of telescope time. The fact that they revealed so much already tells you how powerful Webb is. But Webb is not done with Europa. New observations are being scheduled, different angles, different times of Europa's orbit, different wavelengths. Each set of observations will refine what we already know and possibly reveal things we have not yet imagined. One ongoing question is whether the chemistry Webb detected is uniform across Europa's chaos regions, or whether it varies. So far, most of the detailed analysis has focused on Tara Regio. There are other chaos regions, Murius and Aran among them, that have similar broken-up appearance. Do they have the same chemistry, or does each one tell a slightly different story? If the chemistry is the same across all chaos regions, then Europa's ocean is roughly uniform. The chemistry on the surface reflects a single source. That would simplify our understanding. If the chemistry varies from one chaos region to another, then Europa's ocean might have local variations, different vents producing different chemistry, different parts of the seafloor reacting differently with the water above. That would mean the ocean is more like Earth's, with regional chemistry tied to specific underwater features. Webb is being scheduled to scan additional chaos regions in upcoming observation cycles. The results will start arriving over the next year or two. They will tell us whether Europa's ocean is one big homogeneous pool or a complex chemical patchwork. Webb is also being used to look for plumes again. The first observations did not detect any, but the team has not given up. Plumes might be variable, appearing only when Europa is at specific points in its orbit. Webb will watch at different orbital phases to see if it can catch one in action. If a plume is ever detected, the implications would be enormous. Direct ocean material thrown into space, available for any passing spacecraft to sample. There is another, more ambitious goal. Webb's instruments are sensitive enough to detect very small amounts of certain organic compounds if they are present in Europa's atmosphere. Methane, formaldehyde, other simple organics. If those compounds turn up in Europa's thin atmosphere, they would be powerful evidence of active chemistry below. Webb has not yet announced detections of these compounds at Europa, but the search continues. Each observation adds more data. There is also the question of comparison with other icy moons. Webb has already observed Saturn's moon Enceladus, which has obvious plumes. It has observed several Jupiter moons. By comparing the chemistry of all these worlds, scientists can identify patterns. What features are unique to Europa? What features are shared with other potentially habitable moons? The comparative study is just beginning. In a sense, Webb is the perfect partner for the upcoming spacecraft missions. Webb cannot land, Webb cannot drill, but Webb can survey large areas, monitor long-term changes, and provide the broad context that close-up missions cannot. Clipper will give us pinpoint detail. Webb will give us the big picture. Together, they will pin down what Europa actually is. Already, after just a few minutes of observation, Webb has shifted Europa from a hopeful candidate to a likely candidate for habitability. With more observation time, it could shift the answer further, possibly even into a confirmed positive direction if biosignature gases turn up in the atmosphere. Europa is being watched right now, with the most powerful telescope ever built, looking for signs that should not be there in a dead moon. So far, Every clue is pointing the wrong way for those who believe Europa is dead, and the next clue may be the one that breaks the case open. Imagine you wake up one morning and the news says it. Scientists at NASA have confirmed the presence of life in the subsurface ocean of Jupiter's moon Europa. Microbial life, simple organisms, but unquestionably life. The proof is in the chemistry. Carbon isotope ratios match biological processing. Complex organic molecules of the type only living things produce. The verdict is in. What happens then? The immediate scientific reaction would be a global celebration mixed with overwhelming demands for more data. Every astrobiologist in the world would want to be involved. Funding for follow-up missions would skyrocket. Plans for a Europa lander, currently shelved, would suddenly be the top priority of space agencies worldwide. International cooperation, already strong, would intensify. The cultural reaction would be even bigger. The discovery of life beyond Earth would be one of the most important events in human history. It would change how billions of people think about their place in the universe. Religious leaders would have to grapple with what alien life means for their traditions. Philosophers would write libraries of books about it. Schools would teach it as foundational fact. Children growing up after the discovery would have a fundamentally different worldview than children before. For science specifically, the implications would cascade for decades. If life arose independently on Europa, then the universe is teeming with biology. The same conditions that produced Europa life must have produced life on countless other worlds. The Milky Way galaxy alone, with its hundreds of billions of stars, would suddenly become a vast laboratory of biological experiments. Most of those experiments would have produced microbial life like Europa's. Some, statistically, would have produced more complex life. Some might have produced intelligent life. The Fermi paradox, the question of why we have not heard from alien civilizations, would become more pressing than ever. If life is common, where is everyone? Why have we found no signs of extraterrestrial intelligence after decades of searching? The Europa discovery would not answer that question, but it would make the question impossible to ignore. Practically, the discovery would also reshape space exploration. The search for life would become a central, perhaps the central, goal of space science. Missions to Enceladus, Titan, Mars, and even more distant moons like Triton would be prioritized for biosignature hunts. Future telescopes would be designed specifically to look for biosignatures on exoplanets. Humanity would commit itself to understanding the distribution of life across the galaxy. There would also be questions about Europa life itself. What is it like? How did it start? Is it related to Earth life through some common ancestry, perhaps carried by meteorites between worlds? Or did it arise completely independently? Answering those questions would require getting samples back to Earth labs. That would mean a sample return mission, which would take decades to plan and execute. The relationship between humans and Europa life would also have to be carefully managed. Contamination would become a critical concern. Future missions would have to be sterilized to a degree no previous mission has achieved. We would not want to introduce Earth bacteria into a pristine alien biosphere. There might even be ethical questions. Does Europa life have rights? Should we leave it alone? Should we study it intensively? Should we try to communicate with it, knowing it is almost certainly too simple to communicate back? These questions seem abstract now, but they would become real and urgent the day a discovery was confirmed. The horrifying part, for some, would not be the alien life itself. It would be the implication that the universe is exactly as full of life as the most optimistic predictions suggested. We would no longer be special. We would just be one of trillions. For others, that would not be horrifying at all. It would be the most beautiful answer the universe could give. But there is the opposite possibility. What if Europa is dead? Now imagine the opposite outcome. Years pass. Clipper finishes its mission. Juice finishes its mission. A later lander successfully scoops material from chaos terrain and analyzes it in detail. The verdict, after careful study and replication, comes back. No biosignatures, no organic compounds beyond what simple geology produces. No evidence of past or present life. Europa is dead. This would be, in its own way, an even bigger result than confirming life, because it would mean the conditions for life are not enough. Think about what Europa has. Liquid water in larger quantities than Earth. Carbon, the building block of biology. Salts and minerals. Energy sources from hydrothermal vents and from radiation-produced oxidants. Stable conditions for billions of years. Every ingredient on the recipe card, and nothing comes of it. No life starts. No biology happens. Despite 4.5 billion years of opportunity, the experiment fails. If that is the answer, then we have a serious problem with our understanding of how life begins. The most popular theory says, life starts from simple chemistry under the right conditions. Earth shows that the right conditions produce life. If Europa, with very similar conditions, produces nothing, then either Earth was extraordinarily lucky, or there is some additional ingredient we have not identified. That additional ingredient could be anything. Maybe life needs a specific atmospheric composition that Europa lacks. Maybe it needs surface conditions where sunlight can drive chemistry. Maybe it needs a particular rock type, or a particular salt mix, or a particular temperature gradient. Or maybe it needs something we cannot yet imagine. Whatever the missing piece, finding it would become the new central question of astrobiology. The search would shift from looking for habitable worlds to looking for whatever rare extra ingredient makes habitability translate into actual habitation. This outcome would also reshape our view of intelligent life. If even microbial life is hard to start, then complex intelligent life is much rarer. Earth might not just be unusual. Earth might be a true outlier. We might be, in some real cosmic sense, alone or near alone. That would be the scariest answer. And not just emotionally. It would imply that humanity is more precious and more fragile than we realized. If life is rare, then we are a rare flower in a vast desert. If we destroy ourselves, the universe loses something irreplaceable. The pressure to survive, to spread, and to preserve Earth's biology would become enormous. There is a subtler horror in the dead Europa outcome. It is the horror of having gotten our hopes up. Generations of scientists have devoted careers to studying Europa, partly in the hope that they might be involved in confirming life there. If the answer is no, all that effort still produced valuable science, but it did not produce the discovery many were chasing. The disappointment would echo for decades. Some philosophers have argued that a confirmed empty Europa would actually be more important than a confirmed inhabited Europa. Confirmed life would be exciting. Confirmed emptiness would force a profound rethinking of biology and chemistry. The empty answer might teach us more about how life works than the positive answer would. We do not know yet which it will be. The honest truth is that the data so far slightly favors the positive direction, but only slightly. Webb has shown us habitable conditions. It has not shown us biology. The next missions will bring us closer to an answer, but they might not deliver one cleanly. We might end up with a grey result. Probably habitable, possibly inhabited, but not confirmed either way. That would be the most frustrating outcome of all, and it is the most likely one for the next decade. There is something deeply strange about Europa that does not get talked about often. It is a moon that has been hiding its own chemistry under a frozen lid for billions of years. Whatever experiments started running in its ocean ages ago have been running this whole time, completely cut off from the rest of the universe. We have only just begun reading what those experiments produced. Webb gave us the first real glimpse. Clipper will give us a much closer look, but neither of them, even combined, will let us see inside the ocean directly. Everything we learn comes from the leakage, the breath of the moon, exhaled slowly through cracks in the ice. Think about what that means. There is a place in our solar system, less than 500 million miles from where you are sitting right now, that has been undisturbed for nearly the entire age of the universe. No one has been there, no spacecraft has touched it, no sunlight has reached it. The water is dark, the pressure is enormous. The chemistry has been running, without interruption, since before life began on Earth. Whatever is happening down there has been happening in private. If there are creatures, they have lived and died for countless generations without any awareness of anything outside their ocean. If there is no life, then the strange chemistry of the place has been brewing in silence, producing whatever it produces for an unfathomable stretch of time. The Webb findings are like the first sounds escaping from behind a thick wall. We hear something. The pattern of the sounds suggests something organized is happening, but we cannot make out the words. We cannot see the speaker. We can only listen and try to interpret. This is unsettling to some people. The idea that there is an entire enclosed world right next door, with its own history, its own chemistry, and possibly its own life, sealed off from us for the entire history of the human species. We never knew it was there until recently. We still cannot enter it. We can only stand outside and listen. There is also something deeply lonely about the picture. Europa, if it has life, has had that life entirely to itself for billions of years. No communication with Earth, no connection with the rest of the universe. Just a quiet ocean under a quiet ice shell, orbiting a giant planet, watched by no one until humans showed up with telescopes. If we someday confirm Europa life, we will be the first beings in the universe to know about it, including, presumably, the life itself. Whatever lives there has no way to know about us, no way to know about Earth, no way to know about anything beyond the rocks and chemistry of its own ocean. We would be looking down on a world that does not know it is being looked at. That asymmetry between our awareness and theirs is part of why Webb's findings feel so significant. We have begun to know about something that does not know about us. And the more we learn, the more strange and possibly alive that thing turns out to be. Some scientists have used the word horrifying to describe the implications. Not horrifying in the sense of being scared, horrifying in the older sense of being deeply moved by something vast and difficult to fully grasp. The kind of horror you feel when you realize how big the universe is and how small you are inside it. Europa has triggered that feeling for a lot of people. The chemistry Webb found, the active chaos terrain, the hidden ocean larger than Earth's, the possibility of life. It is all unsettling in the best possible way. The story is not finished. The findings are still arriving, but the picture is sharpening. For every question Webb has answered about Europa, 2 new questions have appeared. That is how good science works. Every discovery opens new puzzles. Here are some of the biggest puzzles we still cannot solve. Why is the chemistry of Tara Regio so unusual? Webb confirmed the presence of carbon dioxide, sodium chloride, and hydrogen peroxide in concentrations that do not match standard models. We do not know what specific process is producing this exact mix. Other chaos regions might have different chemistry, or they might have the same chemistry. We do not know. How thick is the ice shell, really? The estimates range from a few miles to nearly 30. Juno's measurements gave us a working number around 18, but with significant uncertainty. Until we have ice-penetrating radar from Europa Clipper, we are still guessing. How does material actually move from the ocean to the surface? Chaos terrains seem to be the pathway, but the exact mechanism is unclear. Is it sudden, catastrophic breakthroughs? Slow convection? Liquid pockets within the shell? Probably some combination, but the relative importance of each process is unknown. What is the seafloor like? We have never seen it. We do not know what kind of rock is down there. We do not know whether hydrothermal vents are active. We do not know whether the chemistry between rock and water is similar to Earth's or radically different. What is the ocean's pH and chemistry in detail? Modeling gives us a range, but the range is wide. The actual values could shift our predictions about habitability significantly. Are plumes happening or not? Hubble saw possible plumes. Webb has not. The picture remains conflicting. Some plumes might exist but be variable, or they might not exist at all. Is there life? This is the biggest one. Every piece of evidence so far is circumstantial. habitable conditions, strange chemistry, geological activity, but no direct biosignature. The answer might come in the next decade. It might not. Beyond Europa itself, there are larger questions. Is the Europa story representative of other ocean worlds, or is it unique? Saturn's Enceladus has plumes and probably hydrothermal vents. Saturn's Titan has lakes of liquid methane. Jupiter's Ganymede has a deep ocean sandwiched between ice layers. Each of these worlds might have its own version of habitability. Studying them all will give us a population of test cases. If habitable conditions exist on multiple moons in our solar system alone, what does that say about the universe? Is every star with rocky planets and icy moons likely to have at least one ocean world hidden somewhere? If so, the universe is full of potential habitats, and the question is just how often those habitats produce life. There are also engineering questions. How do we eventually drill through Europa's ice without contaminating the ocean? How do we send a submarine through the shell to explore the water directly? What kind of probe could survive Jupiter's radiation long enough to do meaningful work on the surface? These questions will take decades to answer. They will require generations of scientists, engineers, and explorers. The Webb findings are the first chapter in what may be the longest scientific story humanity ever writes. We are not racing to a finish line. We are settling in for a marathon. Europa is the first stop. The other ocean worlds are next. After them, the moons of nearby star systems, when we have the technology to reach them. The horror, the wonder, and the patience this will all require are inseparable. We have started the search. We are not going to stop. Now we come back to where we started. James Webb pointed its mirrors at Europa for the first time, and what it saw was, in the words of some who worked on the data, horrifying. The horror is not in any single finding. It is in the totality. A moon with twice Earth's water, chemistry rising from a hidden ocean, salt and carbon and oxidants pooling in regions where the ice has been broken open recently. A surface that rewrites itself faster than radiation can destroy it. A shell that breathes. A possibly active seafloor with hydrothermal vents. All of it sitting 500 million miles away, completely undisturbed for nearly the entire history of the universe. Any one of these findings, in isolation, would be a major discovery. Together, they paint a picture of a world that is not just possibly habitable. They paint a picture of a world where every condition for life appears to be met, where chemistry is actively running, where the chaos of geology brings the deep up to where we can read it. We do not know if there is life there yet. We may not know for another decade or two, but we know much more than we did before Webb. Look, the shift in scientific opinion has been measurable. Before the Webb observations, Europa was considered a leading candidate for finding life beyond Earth. After the observations, it is generally regarded as the leading candidate. The chemistry confirmation moved the needle. If you ask the scientists who work on Europa what they personally believe, you get cautious answers. They will not commit. They cannot commit because the evidence does not support a definitive statement. But off the record, in private conversations, many of them think the odds favor a positive result. The conditions are just too good. The chemistry is just too rich. The geological activity is just too suggestive. Imagine the moment when the result actually comes. It might be a Tuesday morning in 2035 or so, a NASA press conference, or it might be a paper in the journal Nature with measured language and careful caveats. The headline writers will figure out how to make it dramatic. The scientific community will fact-check it relentlessly. Other teams will try to replicate. And eventually, if the evidence holds, the world will accept the new reality. We are not in a position to know now. We are in a position to be patient. But the strangeness of where we already are should not be lost. 2 decades ago, Europa was a vaguely interesting moon. Today, after Webb, it is one of the most studied worlds in the solar system, the focus of 2 major spacecraft missions, the subject of intense scientific debate. The science has moved faster than most scientific stories ever do. The next chapter is being written right now by Webb, by Clipper, by Juice, by ground-based telescopes, by laboratories on Earth running experiments to simulate Europa's chemistry. Thousands of people in dozens of countries are spending their lives trying to figure out what is under that ice. When the answer comes, it will be one of the most important sentences ever uttered by a human being. Either we are not alone in our own solar system, or we are alone in a far stranger way than we ever expected. Either result is permanent. Either result rewrites the textbooks. Either result changes what humanity is. We are watching the experiment finish. The data is coming in. Webb has shown us where to look. Clipper is on the way. The world below the ice has been quiet for 4.5 billion years. It will not stay quiet much longer.